Good afternoon. Hello, everyone, and welcome to today's first live stream event, which is a Q&A panel. So today we'll be hosting 5 guests. One of them is jumping in shortly if thought 1 p.m. was 1 p.m. South Australian time. So we have with us today Michael Mathiazzo, Dwayne Hamaker, Claire Kenyon, Neil Creek, and Rod Hill. The team will be able to answer any questions that you may have from comet discovery, cultural astronomy, astrophysics, meteorites, astrophotography, solar eclipses, and any other general astronomy questions you might have. Following the Q&A panel, we'll be drawing our third raffle for the weekend, which is for the 1-year subscription to Australian Sky and Telescope. So I will now bring our guests in. So we have Dwayne, Michael, Claire, and Neil. And Rod will be joining us shortly. Hi, guys.
Hey.
Hello.
So what I might get you to do is we'll start with Michael and we'll work our way around. Michael, if you'd like to tell us a little bit about what you do.
Yeah, certainly. I became a comet enthusiast after witnessing Comet Halley from my hometown in Adelaide way back in 1986. And in 1990, I joined the Astronomical Society of South Australia and had the privilege to meet one of the greatest visual comet hunters of all time, a chap by the name of Bill Bradfield. He was my mentor and gave me a lot of support. And my only near success was making an independent discovery of a comet in 2000 that missed out by 24 hours. But in 2003, I gave up visual hunting in favour of comets, searching for them online using Swan Comet Tracker maps. And I had first success came in 2004, and my final success was probably the best one. It was earlier this year in 2020, and so I've got a total of 8 Swan Discovery credits. I have been a past president of the Astronomical Society of South Australia back in 2005 and 6, and currently I'm a member of both ASA and ASV. I'm one of the coordinators of the Vic South Star Party, which we hold annually in October, but unfortunately we're missing out this year. And so currently I reside in Swan Hill, which is a regional town in northern Victoria, where I can pursue my astronomy interests in dark country skies.
Beautiful. Now, Dwayne, would you like to tell us a little bit about what you do, where your expertise lies?
Hi, everybody. My name is Dwayne Hamaker. I'm a cultural astronomer. I'm from the US originally. I did my undergrad in physics, and I came to Australia as one of those sort of semi-annoying study abroad students, I don't know, 17 years ago, whenever it was now. And I fell in love with Australia, and I moved back a couple years later in 2006 and did my master's in astrophysics at UNSW. Just became enthralled in the crossroads of astronomy and culture and decided to do that for a PhD. And since then, for about the last 12 years, I've mostly been working here in Australia, working for different Aboriginal and Torres Strait Islander communities to learn about their star knowledge and help produce some educational materials and research and mentor Aboriginal students in this space, but also working in the larger area of astronomy and culture with respect to things like meteorites and archaeoastronomy and other cultures around the world.
Thank you. Now, Claire, would you like to tell us a little bit about what you do?
Hi, I'm Claire. I'm an astrophysicist working at the University of Melbourne. I'm actually currently trying to finish my PhD, and that has been a 5 or 6 year story. So anybody that thinks things are lasting longer than you think, I know about that. I study AGN, so they're basically really big galaxies with supermassive black holes right in the center that for whatever reason, get really, really hungry and eat a whole bunch of material and shine really brightly. So those at AGN, or you might know of them as quasars. So I also work at the University of Melbourne in teaching and outreach. I run a program called Telescopes in Schools, which is just what it says on the tin. We put telescopes in schools and help schools run observation nights. And I'm currently building a science outreach presence in media. It's one of my big passions under Red-Lipped Astro. And I'm very, very, very focused on destroying these stereotypes of women in STEM and astro, and really just promoting being what you can see, because you can't be what you can't see. And I think young women need to be able to see all of us out there having some success. So I'm really passionate about that.
Okay, and Neil, tell us a little bit about what you do.
Hello, everyone. I'm Neil, and not Noel, Mark.
Not Noel, no.
Clear that up.
We've already had a comment saying that it's too early for the Neil Noel drinking game.
I'm Neil. I'm a professional photographer. I've been doing that for about 15 years now, and I'm a lifelong amateur astronomer. I've been into that ever since I was a kid, and my dad showed me Carl Sagan's Cosmos. When I was 16, I made my own telescope, including grinding and polishing the mirror, which was a very interesting experience. And I've gotten into astrophotography in the last 8 years or so, when digital technology really caught up and has made it possible to do amazing things with amateur and hobbyist equipment. I've been fortunate to have been awarded a category in the David Malin Awards, the National Astrophotograhy Awards, 3 times now. And I've had my work published all around the world, including in Discover magazine in the US and Australian Geographic magazine. So that's very gratifying to have my work seen around the world. So I've got specific interest in astrophotography, and I'm the astrophotography coordinator at Mount Burnett Observatory. So any astrophoto questions, I'm happy to take those. And I've also got a fairly good general knowledge of astronomy. So if there's anything that the other guests can't or don't understand or don't have in their particular knowledge toolkit, I'd be happy to have a crack at it.
Wonderful. Okay, so I'm going to kick things off with the first question, and I'm going to throw it at Michael. What equipment do you use to look for the comets that you look for?
That can vary, obviously. If it's relating to swan comets, firstly I detect them in the data, and the actual swan data, if it's visible in swan, it's at least 11th magnitude, so they're easy to pick up. So all you really need is a 200mm zoom lens and a Canon camera on a tripod. I also use a Star Adventurer mount, which is very handy, and aim it to that particular part of sky and snap away and hope for the best. Hope that the object exists and it's not a false positive.
Wonderful. All right, so I'm going to pop a question up here, Dwayne, and this one's for you. Do you have any recommendations for primary teaching materials related to our First Peoples and astronomy?
Yes. So about a year and a half, 2 years ago, Marcia Langton led a major project to integrate Indigenous knowledge into the Australian national curriculum, and this tied into fire, water, and astronomy. So we produced a whole series of modules, 14 modules on the subject for all subjects. So English, math, science, geography, technology, art, whatever the 7 are, for years 5, 6, and then 7, 8. So primary and secondary. And that was a project that was initially kicked off by Prime Minister and Cabinet, but now is housed at the University of Melbourne. So if you want access to that, the modules include information about a project that's tied to the curriculum for each of those subject areas. It includes a couple of pages of background information for the teachers. It ties in specific activities with outcomes aimed at the curriculum itself, and brings in a lot of really interesting stuff from different perspectives. If you want to get access to that, go to our website at aboriginalastronomy.com.au. On the front page, you'll see that. That takes you into the University of Melbourne system. You can also access the modules for fire and water as well.
Wonderful. Okay, so Claire, I have a question for you from one of the comments. I'd really like to learn, what is the difference between an astronomer and an astrophysicist?
Cool. Okay, I'll give this a go. For some people, they will swear black and blue, there is no difference. And look, I'm going to put it out there. Mostly astronomers say that. I'm joking. If you look at the words astronomy and astrophysics, astro is obviously sky, so sky or stars, that sort of thing. And, you know, if you look at the root words, onomy is sort of like name. So we typically think about astronomers, this is where people draw the line, astronomers as people that categorize, that name, that sort of thing, and that physicists are more interested in sort of the nature of things, so how they work, matter, energy, and their behaviours. I would say, honestly, astronomers are doing astrophysical work, astrophysicists are doing astronomy work. Personally, for me, I'm not sure that it actually makes a huge difference which one you want to be called, but some people do hold very tight onto which one they are and they identify with. But structurally, really, there probably isn't that much difference, except, yeah, if you want to go into sort of actually categorizing and naming things and putting together a star catalogue and looking for certain things in the universe, you probably go for somebody that calls themselves an astronomer. If you want to find somebody that can explain how a black hole moves things around it, or, you know, lensing and things like that, you might, or how it actually works, you're probably looking for an astrophysicist.
Wonderful.
Astrophysicists are less likely to have actually looked through a telescope.
Hey, I've done both. All right, come on.
All right, so Rod has joined us. So Rod, you're on mute there at the moment, Rod, but thank you for coming along. And I'm going to put you under the pump straight away. We have a brand new member who joined us from Brazil on Friday, would you believe, all because of all of these live stream events. And he's got a question for you, Rod. I am from Brazil. I love astronomy, have since I was 16 years old. I'm now 49. I'm a physio and did 1 year master's in, I'm saying it's astronomy, in Australia. My question is, if you would like to become an astronomer, how would you start with regards to courses in Australia? So how do you become an astronomer in Australia?
Well, there are a lot of options, really. In fact, really a lot. Most of the research universities and major teaching research universities offer courses in astronomy, or variously called physics or cosmology or something like that. And they're offered at undergraduate level as majors in physics and mathematics, or they are offered and also offered by some of the universities as PhDs and master programs. But for example, the Australian National University offers a number of degrees. So does Macquarie, Monash, University of Queensland, Charles Sturt, RMIT, the University of Adelaide, and University of Western Australia. To become an astronomer, you need to have completed a degree in science at a university with a major in astronomy. So as a feed into that postgraduate course. Now, to work as a professional astronomer, it's almost obligatory to have a PhD in an astronomy-related field from a major university. So it requires postgraduate work. But I don't want to consume too much time of the panel's time, but if you wanted to quickly search on the web for universities offering astronomy courses, you'll get a very comprehensive rundown of the course names, when the courses start and things of this sort. Bottom line, a lot of the universities have astronomy courses. They'll all require mathematics and astronomy and physics as a lead-in to postgraduate work, and then after getting a PhD or perhaps a master's as well, or instead, then that would be an opportunity that will open some doors for working as a professional astronomer. Wonderful.
All right, Neil, got one for you. Andrew's been to a few of these sessions, and he's got an imaging question. I've been imaging the planets on my Evolution 9.25 Schmidt-Cassegrain for a while now, and I'm interested in expanding to galaxies. I recently bought a second-hand CGEM mount, and I'm looking at imaging galaxies using a DSLR and ZWO ASI 120 or ASI 224 MC camera, which I could use as a guiding camera. What's the best way of setting up auto guiding with this setup? Right up your alley, this one.
It is, although I will preface this by saying that I don't have a CGEM mount or a Schmidt-Cassegrain, so I'm speaking from what I've read and learned rather than my own experience here. But with a Schmidt-Cassegrain, you're going to be getting very long focal lengths, which is great for shooting galaxies because they're typically quite small in the field of view, but it'll mean that your guiding will be a bit more challenging. The guide scope the guide camera you've suggested is good. You'll need to get a guide scope as well so that you can put that camera on. I recommend the software PHD2. PHD stands for Push Here Dummies. The point being that it's supposed to be very easy to use, and it is by and large. And you need to hook that up to a computer. The computer will then control the telescope based on what the PhD guiding sees in the guide camera. You'll need to work out how to connect the computer to the telescope yourself. I use a Skywatcher mount, and I use some software called EQ Mod to connect to that. But I believe that with as a Schmidt Cassegrain, it's a Celestron mount. I believe that you need to use some Celestron specific techniques to connect to that. I think it might be plugging into the handset rather than into the mount directly. But those are the sort of the specifics that you'll need to do research on yourself. But once you've got all that set up, you'll use your PhD guiding to track a nearby star, and it will be a challenge because of the long focal length. That means your guiding needs to be really spot on. And guiding can be a real challenge to sort of figure out all the little different pieces of problems that you can get. There are a lot of things that can influence it. But my recommendation beyond just getting started yourself is to join an astronomical society that has astrophotographers in them and ask for their advice when you run up against troubles. You're likely to find someone who's done something like what you're trying to do before, and you can pick their brains for their expertise and experience and see what they've been able to do. So if you're in the area of the ASV, there's a very active astrophotographer group there. And if you happen to live in the eastern suburbs of Melbourne, the Mount Bennett Observatory, where I'm from, also have an active astrophotography group. So I'm sure you'll be able to find someone who can help you when you run into trouble.
Yeah, and they're very friendly, the Astro guys, that's for sure. Although I do get in trouble for calling them Astro guys. Okay, got a good question here. What is a gamma ray burst, and what makes them so powerful that you can see them with the naked eye halfway across the universe? Oh, who wants to answer that one?
Who wants this one? I can give it a go if you like.
Yeah,
All right,
sure.
go for it, Claire.
All right, well, you guys can jump in when you're ready anyway. So gamma ray bursts are kind of incredible. They were noticed by a satellite in 1967 that was actually looking for covert nuclear tests. And it's sort of surprising they saw this massive bright flash. And we've seen quite a few now in the sky. Gamma ray bursts are, I like this phrase, exactly what it says on the tin. We get this amazing huge flash of gamma rays, and they are the most energetic things we see in the sky. They can last for less than 2 seconds or all the way up to about 10,000 seconds. So there's 3 sort of different kinds. The short gamma ray bursts, we typically see them 3 out of 10 times, and we typically see long gamma ray bursts, which are over 2 seconds, most of the rest of the time, so 70% of the time. What we think that they are, for the short, we think they're actually different classes of things. So the short gamma ray bursts, the less than 2 seconds ones, we think they're actually binary neutron stars merging. So when 2 neutron stars, so 2 dead stars, basically that have collapsed from supernovae of big massive stars into neutron stars, they orbit each other, and then eventually they actually coalesce into one. So we think that they're the short gamma ray bursts, and the reason we think they're the short ones is because with that time frame, it can't be anything much more massive, because it would actually take a lot longer to produce the gamma rays. So we think that the short ones are binary neutron star mergers, and obviously doing follow-ups with things like gravitational wave observations is a key hot topic at the moment with that. And long gamma ray bursts are the ones that are over 2 seconds. And we think that they're supernovae of very big stars. So when we have very energetic collapsing of huge stars into neutron stars and black holes, they give off this enormous pulse of gamma rays. And then after that, we typically see an afterglow curve, a light curve, which is obviously really interesting for astrophysicists and astronomers in trying to work out if we can, just like in other stars that have light curves, trying to work out distances as well. If we know a little bit about information, the system, we can actually work out how far away they are. Interestingly enough, they're really only found outside of our galaxy at the moment. So, yeah, so they're just fascinating, really, really interesting. And the fact that they're kind of separate classes is also amazing. So anybody else want to jump in there?
I think you covered it off very well. There we go. All right. These are a nice one.
I might butt in if I may.
Yes, go for it.
It's just as well they only occur outside the Milky Way at the moment, because if there was one inside and relatively close, it might be curtains for all of us.
We'd be in a bit of trouble.
Yes.
It's a binary situation, isn't it?
Yes.
So, Michael, what are the naming principles used when a new comet is located?
Yep, that's an easy one. You've got 26 fortnights of the year. You've got 28 letters of the alphabet. Chuck out the I and the Z, and you'll end up with perfectly matching fortnights. So the first comet of the year, if it's discovered in the first fortnight of January, will get the designation A1. So, for example, 2020 A1. And then, say, from January the 15th, it'll be B1 from discovery. So my discovery in late March was F8. So it was the 8th comet discovered in that fortnight period.
There we go. Nice and easy. Okay, this is an interesting one. In 2018, in Mackay in Queensland, I witnessed a spectacular vision with my eyes, so beautiful. It was speechless. Actually, it had a slow-burning, very long trail traveling across the sky like a burning flame. As it went across it, not really falling down from the sky. Could anyone tell me what I saw, as I don't think I would ever see another in my lifetime? What do you think it might have been?
I can have a crack at that.
Go for it.
Generally, something that's moving very slowly in the sky is likely to be space junk. The minimum sort of speed of a meteor entering the atmosphere will be about 18 meters a second, unless you've got a Earth grazing meteor potentially.
Kilometers, you mean?
Oh yeah, kilometers. Yes, yep. Good on you. Yeah, exactly. Yeah, that's why we've got this panel, so we can pick up mistakes. So probably a bit of space junk. Depending on the actual time itself, because we do have regular annual meteor showers that occur on specific dates. She hasn't exactly stated what date she saw that. So
makes it a bit hard.
We can't pin it down to a particular meteor shower.
Here we go. Mackay, July 2018, the 31st at the Parks Caravan Park. So you look. End
of July, we have the Delta Aquarid meteor shower. We also have the Alpha Capricornids, and they are particularly bright. They do actually have bright fireballs, so potentially could have been an Alpha Capricornid if it was at the end of July.
And being in Mackay, she'd be in a pretty decent area to see that.
Yeah, it would have been overhead at that time.
Okay.
Pretty much.
Next one. With a few projects, missions related to finding life, Saturn, Jupiter, and Jupiter moons, Mars and Venus, where do you think it will be found first?
That's the $64,000 question, isn't it? I mean, it could be anywhere. There's a few places in the solar system that have potential for having life on it, but we have a sample of one when it comes to understanding how life forms. So it's impossible to really predict the likelihood of any particular set of circumstances bringing forth life, because we can only know from our own circumstances, and we don't even know now what the particular circumstances were that brought around life on Earth. So I wouldn't be willing to take a bet on where we find it. There's an equal chance that we may actually find evidence from life in an exoplanet before we can get a probe to one of our own solar system bodies by finding methane or other signs of life in the atmospheres of a terrestrial exoplanet. So your guess is as good as mine.
Anybody else want to chip in?
Yeah, I wouldn't mind. Rod Hill here. There's the issue is whether it is, if it's in the solar system, the issue is whether it is a contamination of life on Earth or whether it is a new genetic code that would represent a new genesis, if you like, of life. That's the first point I'd like to make. We've already got, I think, the order of 100 meteorites which have been found on Earth that are actually, by the composition of the gas bubbles in them, indicative of the Martian atmosphere. So we know that cross-contamination can occur, and it's likely to have happened in the other direction as well on Mars. In other words, pieces of Earth blown up by a collision with an asteroid or something, blown out of the Earth's gravity filled by a collision with an asteroid or something, could have landed on Mars. And so if our first discovery of life on Mars occurs, it is not necessarily likely, but there's a very good chance that it would be a contamination from Earth. And it would only be if you could bring the samples back and do DNA fingerprinting on them to establish whether it in fact was similar, if not identical, to life on Earth, that you'd be able to confirm it as, if it didn't happen that it was identical, then it would be another example of life forming in its own right. I have to say that some recent work's been talking about some of the planets in the outer solar system and their potential for liquid water under the crust of solid material. It's some recent work on the genesis of life as we know it has indicated that you actually, if there's only water and the molecules don't dry out and wet and dry out and wet, that the chances of forming long chain polymers of the sort that are necessary for the origin of life are much reduced. So having been very excited about looking at things in the sub crust areas of moons like Enceladus or Io or something of that sort, on the big planets in the outer solar system, having been very excited about those, we're now starting to think that maybe they don't have the conditions that are conducive to the formation of microbial life. And I'll finish by saying, and there's a big distinction between finding microbes somewhere and finding intelligent life. The arguments for microbial life forming are quite strong, and it's very likely that somewhere we will find that. But the arguments, I could wax lyrical about this, the arguments for intelligent life elsewhere are much less likely, despite them billions of planets that are likely to be observed in a Goldilocks type zone. There are a lot of other special conditions that have to take place for that life to evolve into something that's intelligent enough to provide communications with us, or industrial gases that will fingerprint their atmospheres when we look at exoplanets and that sort of thing.
Wonderful, great answer. We have another one here for Claire. I've heard about the STEM project with Lisa Harvey-Smith. I agree with you, women getting involved with science. Good on you and good luck, Denise. There you go. I thought that was a nice one to pop up. It is good to see women astronomers, that's for sure, and astrophysicists and scientists in general. It was very good to see Sadie do her little presentation yesterday as a 7-year-old girl who wants to get into science as well.
Thanks, Denise. I just want to add to that, Mark. There's a really great thing on at the moment called Superstars of STEM, which is I think it's 20 women across Australia who get supported to actually do science communication and everything else, everything related with that. And applications have closed, but it's worth just looking out for that because it's a 2-year mentorship thing. So stuff's happening everywhere, and it's an absolutely amazing time to be involved.
Wonderful. Now, here's a good one. What do you believe Beetlejuice will leave behind when it goes, or if it already has gone supernova? Do you think it will be a neutron star or something else?
Well, I think the question here is actually they're probably arguing less about what's going to be left and more about when it's going to go, why we think it's going to go, and also what's going to happen when it does go, because as people probably realise or probably know, Beetlejuice is sort of pulsating at the moment, so it's kind of getting dim, and we think that is a precursor to its going supernova. So Beetlejuice is a red supergiant in the constellation of Orion, and I think Dwayne could probably comment a little bit about, I think there's some history of Indigenous astronomy recognising Beetlejuice actually in Orion. I don't mean to put you on the spot, but I'll cross you in a minute. But basically, they think maybe it might go in the next, 100,000 years or so. Who knows? Could be tomorrow. Could be not in any of our lifetimes. And when it does go, we're expecting it'll go supernova and shine as bright as probably about half the moon for about 3 months and be visible in the daytime for a year or so. Now, the reason it's interesting is because we don't really know with the pulsating how big it's going to be when it goes. So with pulsating stars, they don't always pulsate in unison, okay? So with Betelgeuse, what's actually happening is it's actually got whole scale pulsating. So the moment that it goes supernova, it will have a radius of whatever the radius is. And the radius is going to be the thing that dictates how it behaves when it goes. So it could be at its big part, the whole star, with a massive radius of about 700 times our sun's radius, or it could be a little bit smaller in its sort of more collapsed form. So scientists have recently been arguing about that. There've been a couple of papers out this year about what might actually happen, what the supernova is even going to look like. And then typically, I guess, we'd be left with some sort of glowing remnant, possibly. It just depends on how much material is left after the supernova. So in order to answer that question, you have to also say, well, what's the supernova going to be like? Because if a supernova is really explosive, it'll lose a lot of material, which will then stop it becoming a neutron star, for example. So, yeah, your question is great, but we have to answer the first one first.
Anybody else want to add to that? No,
I know sorry? What was that?
What was that, Dwayne?
So there was quite a bit of excitement, end of last year when it started going through its dimming period, and it was a great opportunity for everybody to see that, this is something we can see very clearly with our naked eye. You don't have to be a super keen, trained observational astronomer to be able to see this necessarily, because these events, do happen on occasion. And, we find that, Aboriginal people had recorded this in their oral traditions a very long time ago. And I know that one of the things that people were getting excited about was, did people want it to go supernova? I mean, you were going to see something quite amazing in the sky, as Claire said, potentially half as bright as the moon, visible for quite a long time. But then when it goes, it's gone. You're not going to see it anymore. Orion, as we tend to think about it, is not going to be there. All the constellations around the world that had that as an anchor point, that star is gone. So it's kind of weird. I remember thinking about that and debating it. And, my own personal preference. Do I want to see it go supernova and see one of these amazing, extremely rare astronomical events, like a nearby supernova, knowing that the following year, that's it. It's gone. You're never going to see it again. You'll be telling your grandkids about this star that's no longer there. It's going to be strange. And it's just
Orion would look so different without Betelgeuse.
Yeah.
What was that?
Orion would look so different without Betelgeuse.
I know, right?
Right, so we have another good one. Are there any groups, events in Victoria when COVID restrictions aren't in place where we can learn more about Indigenous Australian astronomy?
Yes, and you can certainly learn about that now, even with COVID restrictions. I mean, obviously being able to get outside and see things is great. A lot of the communities across Victoria still maintain very strong traditions about star knowledge. And I've been very privileged to hear a few of those. Uncle Wayne Thorpe is a Gunai Kurnai custodian who lives out of Lake Tyers, out near Lake's Entrance in Gippsland. And, he talks about the Milky Way being a river and there being this chase between the emu and a man and a tree falling over the river. I'm not going to go into the details of the story necessarily. It's not my story to tell, but how these characters go into the sky and how they relate. And that tree that crossed the river is the Southern Cross, which when we look out in the sky spans that little band of the Milky Way right there. And how the emu hides away from the hunter who became the moon. So whenever the moon comes out, the emu goes away until the moon leaves and it comes back out. And of course, what they're describing is the sort of the light pollution caused by the moon blinding out the emu. So you see these dynamics in the old traditions. And there's a student that I'm working with here at the University of Melbourne, because Claire and I both work in the School of Physics. And it's a Yorta Yorta person who's doing an ecology degree. And they're looking at the link between the plants and the animals and their connections to the stars, mostly in Kulin Nation, so sort of central Victoria, south central Victoria, and also how that's linking into climate change, because when the stars rise and set and how it links to the behavior of the plants, animals, and seasons is very linked, very closely together. But because of climate change, it's all going out of sync. So you can not only measure that change to see the effects of climate change, but also to be able to work with the Aboriginal people who've been managing this land for tens of thousands of years, forever essentially. And we can learn a lot from that, because Victorians have gone through a lot of original Victorians have gone through quite a few major events in history, from ice ages and rising sea levels, the formation of Port Phillip Bay, things like that. There's a lot we can learn from that. So if you go to our website at aboriginalastronomy.com.au, you can find some information there. Boron stuff is pretty well known. You can find that on our website, as well as all the stuff we're doing here with the Kulin Nations.
Wonderful. Okay. Where was it? There was another good one that I found here that I want to pop up. Here we go. Is it a possibility there was another universe before 13.8 billion years ago, before the Big Bang?
First thing I want to say regarding that is that time appeared at the same time as the Big Bang. So the word before is kind of irrelevant. You can't have it before time existed. Time is something that we have in our minds. It's ingrained in who we are. There's always a before and after. But if time doesn't exist, there's not a before either. So that in a way kind of invalidates the question straight off the top. But there's a lot of ideas about there being multiple universes, and we don't really have any evidence to support that. But there's a lot of maths that says it's possible.
Anybody else want to add to that?
I think it's one of those questions that get a lot of people into astrophysics and into this sort of thing, so we can try to find new, innovative ways of tackling that kind of a question. Because I think I read recently that despite what I always thought, there was no way of being able to test that, there are certain ways you can start to test some of these hypotheses. And that's, I think, where it gets really exciting, because I've been in astronomy my whole life, and I didn't even know that. I thought there was just one of these purely theoretical ideas, and it turns out there actually are elements of that you can test. So, it really brings in a totally different way of trying to conceptualize how we understand our universe. As Neil said, when does time start? When does it end? What the hell even is time? Are there multiverses? It's an exciting question, and I think it's a reason that at least some people get into the field itself.
And a reason some of them get out.
It's not an easy question to grapple with by any means.
All right, so we've got another one here. What is dark energy? How much of it exists? And what impact does it have on our galaxy?
If any of us could answer any of those questions, I think we'd be getting a Nobel Prize.
Any theories, any thoughts, any ideas?
I'll chime in here.
Rod, go for it, Rod.
Okay. All right, thanks. We're struggling to explain either dark energy or dark matter, for that matter, and the two are, while different, are sort of linked in a way. And some of it comes down to whether the universe is expanding or not, and whether it's going to go back to another big crunch, or whether it's going to expand indefinitely and just get further and further and further away. And part of the discussions at the moment around that are that if we needed to bring up dark matter because of the form of galaxies, that there wasn't enough visible matter in galaxies to explain their shape and their rotation speeds and so forth. So dark matter had to be brought in to explain some of those galaxy formations, shapes and so forth. And if there's a huge amount of dark matter, as well as the visible matter, if you like, then the universe would ultimately slow down, because gravity would ultimately become dominant, and there might be a turnaround in the expansion of space to produce another singularity and maybe another Big Bang forever to repeat itself. On the other hand, if dark energy is dominant, then it will overcome gravity, dark or otherwise, and the universe would continue to expand forever. And we would have a very lonely end in trillions and trillions and trillions of years. So it has some fascinating implications, although we don't know enough about it, about either dark energy or dark matter. It has some interesting implications about the future of the universe as we know it.
I think I would just add as well that when we talk about dark matter and dark energy and normal matter, the reason we lump them all in together is because we talk about matter and energy being sort of two sides of the one thing. So when we sort of talk about the numbers, we say, you know, there's 68% of the universe is dark energy, 27% is dark matter, and the rest is normal matter. So most of the stuff that we can see is actually only a tiny percent of what actually exists. So we lump all that in together as an energy mass description of our universe, and that's why Rob was talking about dark matter and dark energy in the same sentence, and that's really important that we keep that in mind. On the whole, for anybody that's probably hasn't heard of this before, and I know that there are people out there, dark energy we think is some sort of force that is kind of almost like an opposite to gravity in a way, some sort of field that forces everything on the largest scales in our universe apart. So we think it's slightly less than what's called the cosmological constant, but people think that might be a candidate for dark energy. It's essentially the reason we think things are flying apart in the universe. Now, it's important to remember that's on the largest scales. So like Rod was talking about expansion of the universe, and it's not really expansion of galaxies or anything. So to get to your question about what impact does it have on our galaxy, when we're talking about things that are gravitationally bound, very little. But when you step back and look at the universe as a whole, which asks another question about, it goes back to time starting and, you know, the scale of the universe. You can't really step back from the universe at all, but you're always in it. But when you are, sorry, I just saw a cattail. When you are looking at the universe, it's expanding in all directions. It's a large scale phenomenon that we see dark energy acting over.
Wonderful. All right. So Claire, you can continue on because this one's from Sadie, age 7. And she wants to know, how old were you when you became interested in astronomy, and did you always want to be an astrophysicist?
Hi, Sadie. Thanks for tuning in. It's really nice to have our audience so young. It's fantastic. Yeah, look, I think when I was a kid, I pretty much liked everything. I was into dinosaurs. I was into space. I was into chemistry kits and growing crystals, that sort of thing. So I've always just been, you know, all the pies I could find, I was in them, right? But I think when I was 2, actually, and for people that can do their maths, don't calculate my age. When I was 2, my mum took me out to have a look at Comet Halley in the sky, and it was, of course, overcast, so we didn't get to see it. But, you know, that was my first astronomy passed on from my mum. And then when I was a teenager, I went out to see one of the meteor showers that happened, and I snuck out in the middle of the night. And I stood on a really big fat drawing pin, and it went right through my toe. I didn't even notice. It's just this clinking noise. I was so cold and everything, and I went out and it was really cloudy, and I was really disappointed about that. So I actually stopped doing astrophysics for a while and astronomy for a while, but I've always been really fascinated in just looking up at the sky and just how beautiful it is, I think, and that's one of those things that I think everybody feels. You've got to be a robot to not feel that when you look up at the sky. And I actually started off in a music degree when I went to university. So I came back to astro like a lot later, and I love it now. But I think just being excited about everything is the best way to be. So you just get into everything and you find out what you really want to do later. And then you go, oh, yeah, I wanted to do that when I was 2. Well, that's just, you know, you just connect the dots later.
Wonderful. Now, Michael, we have a question for you that's wanting to know, what are comets and where do they come from?
Okay. Now, if you think about our solar system, the sun's the bright thing in the middle, and you've got your planets, your rocky inner planets, and your gassy outer planets, and your very icy extra outer dwarf planets. So asteroids developed. They're all the leftovers from planetary formation. They developed in the inner part of the solar system. And there is a transition as well where you get comets / asteroids. So asteroids that have a bit of water ice in them, but they're mainly rock and stone. And so the further out you go, so beyond Jupiter, you start to get more ice and gas. In the Oort cloud, which is the sort of reservoir of comets that are well beyond our boundary of the solar system. The Oort cloud expands out to 100,000 astronomical units, so it's absolutely gigantic. And it's also distributed in a circular, spherical shape. So that's why comets can come in at any time. They get bounced around and get flung into the inner part of the solar system where they get bright. Depending on how lucky we are, the closer the comet gets to the sun, the brighter it's going to be. So whenever there's a new comet discovered out there, we eagerly await the calculations of its orbit and find out if it's going to get close to the sun. So hopefully that's hope I've explained all that.
It's a good explanation. Okay, so we have a question from Andrew. We see lots of pretty images of the planets where the colours bear no or little resemblance to their real colours. Hubble is the worst of this. Is there any work going on to measure the actual colour of planets? Anyone pointing in and an imaging spectrophotometer, a photometer at the planets? Sorry, I had a big night last night.
I think that there is absolutely much research going on about the colours. The main reason being, of course, is that colours correlate directly to the materials that make up the planets. Jupiter's a good example. When you look at the cloud bands, you can tell that they're different materials from one cloud band to another. Most of the photos that come from NASA actually come unprocessed. Well, all of the photos come unprocessed, and NASA selects a few that they want to do some work on to share with the public. The ones that they're doing their research on, they get processed in different ways to make them useful for their research, but they generally don't get published. A lot of stuff these days, though, from NASA, because NASA makes all their photos available to the general public, all the raw data, is that many hobbyists are processing those photos and sharing them. And NASA likes the results that they're getting from those processing so well that they share them on their social media. And not to say that there's anything wrong with it, but a lot of people who are amateurs and in the general public who process photos, they like punchy, contrasty, highly saturated images. So that's what you tend to see more of these days. But it's a bit sort of it's hard to say what's right because no one's been there to see things with their own eyes. We can measure the wavelengths of the colors and such, but the way we perceive color as a human being and our brains perceive color is very subjective. It varies from person to person, from the time of day, the light that you're experiencing, even your mood. If you're a photographer, you know the feeling of processing a photo at night, going back the next day and looking at it and going, oh, what was I thinking? That looks terrible. It can change from moment to moment. So there is absolutely scientific work being done based on these observations, but people love having a lot of fun to make beautiful, vibrant colored images from the NASA raw data.
There we go. All right. We lost Rod. I'm not sure what happened there. Okay, so now we've got another question. Why is the moon considered such a mineral resource? Surely there are preferable planets, moons much further afield which are better candidates, keeping in mind, of course, the time involved in setting up the moon for mining versus the possibly shorter time it will take to find such further away candidates. Who wants to have a go at that one?
Well, I think the answer is in the question. The moon's a lot closer. It's a lot more easily accessible. Yeah, there are asteroids we could pull in and have a whole range of materials. I mean, there are exoplanets where it rains diamonds. Sure, we can grab one of those somehow, but the moon's right there. We've been there. It's it's the only place humans have been to outside the Earth. So it's more easily accessible, and because a lot of the material from the moon is the same as the material on the Earth, it's not the only reason, of course. Asteroids have other things we need as well. But in reality, it's right there. It's like walking across the street versus trying to drive to the next city.
Just to add,
I think also.
No, you go ahead.
Sorry, go ahead. I was just going to say, Dwayne, you're quite right in terms of cost, but also and human cost as well. You're right. We haven't been anywhere else except for the moon. We've been to the moon quite a bit. We probably know the most about it than we know about anything else. But also, space travel isn't easy. It's dangerous, and there's never 100% surety that people are going to return. And so to go somewhere we've been before that we kind of know a little bit more about how it all works is going to be the first target every time. With every bit further you have to travel in space, you're looking at fuel, which is really expensive, and also human cost as well. So that plays into it in quite a big way, I'd say.
Just to add to all of that, though, as well, firstly, there is some resources on the moon that aren't available on the Earth. Helium-3 being an example of that, which is expected to be a fantastic fuel for the future of fusion reaction, which is a really exciting potential technology for energy generation. But on the contrary to that, there actually are some projects being under development for exploring, capturing, returning, and mining asteroids. As we see more and more private industry getting into the space race, you're going to see a much greater diversity in the kind of interests and activities that we're doing in space. I've seen quite a few different projects that are currently well under development for launching asteroid capturing space probes that can approach a target asteroid, lock onto it or sort of connect to it in some way, and using various techniques to bring it back into an Earth orbit so we can extract the minerals from that location rather than having to go all the way out and all the way back from its original orbit. So these are all really tricky technological things to do, but there is a lot of interest because, I mean, space is going to become the next gold rush. There's so much potential to make money out there. And so a lot of people are very interested in finding their own way of doing that. And who knows which will be the most successful and the most profitable, which is what drives it all.
I think as long as we don't name that asteroid capturing device Wormwood, we'll be safe.
Rod's back. Sorry, we lost you there for a second. Did you have anything to add to this question here about why is the moon considered such a mineral resource? We've probably got time for maybe 2 or 3 more questions after this one. So,
well, thanks for patience. It must be the COVID restrictions in Victoria stopping coming in. The Wi-Fi failed for a moment. Yeah, look, the moon's an interesting body. There's been some suggestions of water on some of the permanently shadowed, the floors of some of the permanently shadowed craters in the North and South Poles. But otherwise, it hasn't got a lot of water in it. And also the rocks are quite interesting. They don't have the same sort of composition, for example, as Earth nor Mars. So it's probably not the best place in the world by some people's reckoning to extract mineral resources relative to, say, Mars, which seems to have a crust more similar to Earth in terms of the abundance and an amount of and concentrations, relative concentrations of the elements that are important to for our industrial world. So probably Mars isn't going to be the most, but there are some asteroids that are very rich in particular rare earth and precious metals and things like titanium and zirconium and so forth. So they, as someone I think said towards the end there when I came back in, the asteroids may represent a better prospect for off-Earth mining.
There we go. All right, so we've got a double whammy here. I'm going to put both of them up. I can only put one up at a time. But both are talking about the movie Contact. So Sergio, our Brazilian member, he's currently watching from Brazil. I have no idea what time it is over there, but I'm sure it's either very late or very early in the morning. Our late Carl Sagan wrote Contact, which became a movie. In the story, the main astronomer pursues life outside of Earth, and she's criticised about it. So he wants to know, where's the next part of it? Do you think it's worth as society and astronomers to spend money and time to pursue this? And then Gavin, who's an ASV member as well, I've recently rewatched Contact. How much scientific effort is going into SETI and the hunt for extraterrestrial life? There we go.
Okay. I'll just say I don't know much about the actual funding going into SETI and the hunt for extraterrestrial life, but there are a very large number of different projects now that are either about sending information about us out there which I always find a little bit creepy, or looking for information from places that we think maybe are, well, we're searching for extraterrestrial life. So either putting out signals or getting them back. There's a lot of different groups doing that now. There's, I forgot what it's called, the Futures Project or something. There's a couple, like a billionaire funded one where we're sending out signals, also looking at some real, like cutting edge physics of sending little tiny bots out, which we're talking like it's going to be years and years and years and years before they get anywhere. I'm not a big fan of sending a lot of information out about ourselves. I feel like I'd love it to be fine, and I'd love to be very positive about all of our experiences with everything. But if there's one thing I know about human beings after my life on Earth, is that sometimes you better to proceed with caution. And I think broadcasting information about yourself may not always be the best option. To get back to Sergio's, thanks for the question, Sergio, about the, I guess it's an ethical question. It's a philosophical question. And it comes back down to me, the same question I get asked all the time. Why do we put money in astronomy? Why do we put money in astrophysics? Why do we bother with science? And there are so many ways of answering this question. But for me, fundamentally, one of the reasons we are on Earth and that we interact with our natural world and we're so fascinated about it is we're getting these great tools to really think about the world around us and to ask questions and then go and find answers to those questions. So I feel like it's wrapped up with the whole why science question. And for me, the most fulfilling answer is because we can and because we should, and it's about building ourselves as humanity. It's part of our job and one of the things that drives us. So finding out if there's other things out there like us or unlike us, I think is part of that question, and that's what we find truly exciting as a race of animals, I suppose. So yeah, I think the money is actually, I don't think there's a lot of money put into it compared to some of the money we put into, to be a little bit controversial here, things like weapons, for example.
Yes.
The money we pour into defense of from other people on Earth is enormous compared to what we pour into just astronomy or astrophysics or any science, actually. So the R&D budgets for waging war on each other and protecting ourselves from each other it far outstrips anything we put into science.
Imagine if we spent that money on science.
I know.
In a very different world.
Imagine if we spent 1% of that money on science.
1% of that money on science. Would anybody else want to add to what we're just talking about there with contact and Sergio's question about the ethics behind it?
I think an important thing to remember is that there are a lot of unintentional benefits from doing this kind of work in astrophysics. I mean, I think everybody here knows, or most people know that Wi-Fi developed from technology developed by astronomers, which I believe was to search for Hawking radiation from black holes. At least that was part of it, I believe. Please correct me if I'm wrong, but a lot of technologies and things that can be both detrimental and beneficial have come from this research. I think Neil deGrasse Tyson published a book mentioning what Claire had talked about, and that's the sort of uncomfortable marriage between astrophysics and the military in the past. But there have been a lot of major societal benefits that come out of scientific research, including astrophysics being a major one, that were nobody ever said, I want to develop this. It's sort of an unintended consequence. But that just shows the holistic nature of everything that we do. We don't work or live or do research in isolation. We may be trying to ask questions in astrophysics, but the solutions to that, the technologies that we help develop, the ethical frameworks around that impact everything else in our lives and the world around us. So I think that even though people may question the need for this sort of blue sky research, or even something that might seem silly like searching for life outside the Earth, there are a lot of benefits that come with that. And there's going to be a lot of research outcomes that come out of that research that weren't intended to find life. Maybe you didn't find life. Maybe you found something else. I mean, even searches for the Loch Ness Monster found all kinds of interesting things in a Scottish lake. They weren't, some dinosaur swimming around in the water, of course, but they were unintended discoveries. Viking longships in the bottom of the lake, or a new species of some kind of worm or something. You know, a point being is when it comes to this sort of work in astrophysics, there are a lot of unintended but highly beneficial outcomes from even blue sky research.
Yeah, look, maybe I could add another point if there's time. The wireless LAN research that involved in Wi-Fi and so forth came out of CSIRO, and it was the radio astronomy group there. You're quite right, Dwayne, on that. But it was CSIRO's work that was discovered in the classic Rembrandt in the attic, as they say. You know, the work that had been done, and it had been patented, but its potential in other areas of application other than radio astronomy had not been realised or thought of. And it wasn't until someone from totally outside that field came and saw what it was capable of that CSIRO suddenly realised, hang on, we're onto something that's really important here. In fact, something that was being used by a lot of the other major computer manufacturers and so forth and so on around the world. We're a bit late and lost, I think, half of the period of patenting of that discovery before it was properly commercialised, and CSIRO started to get what was close to $500 million worth of royalties back from that work. But at the end of the day, the contact movie is an interesting one. I would like to point out, though, that every dollar that's spent is a compromise. Whatever dollar you spend on something is not spent by something else. And I was on the board of the Australian Synchrotron for some time down there in Clayton, in Victoria. And we were asking for more money for beamlines because only half of the spots were available had beamlines on them and available for research. And I was talking to a politician at the time when we were trying to persuade the government to put more money into funding these beamlines. It's about $10 million a beamline at that time. And the response from the politicians, it sounds bad, but it's actually quite true of the difficulty they have. They said, well, how many beds in hospitals are you going to sacrifice in order for us to be able to fund your beamlines? And it's almost a fixed pie situation, and what you take out in one slice is lost for someone else to eat. So they're not easy decisions to make. And I think in the contact circumstance, the federal people in the film, the federal people wondering about whether this was an aggressive life form that was going to come and crush us like we tread on ants here below our feet, intentionally or otherwise, it was a reasonable question to ask at the time. But that's a subject for a huge amount of debate.
I just want to add a very quick point to that too. I mean, everyone's got their own opinion on this, but I've seen research that says every dollar spent on theoretical research contributes $5 or $10 back to the economy down the line. So the point about a limited amount of funds and how you're going to distribute that is very valid, but the accounting needs to take into account the fact that the research money that's being spent is going to get paid back. Spending on military doesn't. It's a black hole, to use a metaphor from our field. So that is a very important side of things that a lot of people fail to consider, is that it's an investment in the future, in not just in our knowledge, but also in the economy.
Wonderful. That's could keep going, couldn't we? We are running short on time. We've got to jump into the solar stream very shortly. So I think we might have to finish it up there, but there's still a heap of questions that we could go through as well. So I think we might have to organise another one of these Q&A panel sessions, because we've got questions about the solar system, why it remains in a constant orbit, questions about astrophotography and stacking images, questions about public events for Indigenous astronomy, how many astronomers and astrophysicists work in Australia, what is the Oort cloud? We have so many questions still to go through, but we are.
I'll endeavour to get to some of those questions in the comments afterwards.
Yeah, guys, all five. If you want to jump into those comments and answer some of those questions, that'd be great.
And I also just want to quickly make the point. Matt H has corrected me that yes, there were actually some significant innovations that came about as a result of military research. So yes, I was mistaken on that point. So thank you for that, Matt.
So just quickly before we all jump off, I'm going to do the raffle for the Australian Sky and Telescope 1-year subscription. And let's see who wins that. I'm hoping we can, yes, we can see the wheel. Wonderful. All right, here we go. We're going to draw
Round
this
and round
one
and round
down.
she goes.
Round and round she goes. And Ian Dodd. Ian Dodd's won it. Thank you. So Ian will contact you via email, get your details, and send you out your subscription. I'll just get a
Congratulations, Ian.
Yes, congratulations, Ian. So everyone, thank you very much for coming along. We're going to close it up now, and in about 10 minutes, not even 10, 8 minutes, I'll be back with the solar stream. We've got some clear skies. I'm just looking at the skylight at the moment. And Russell from the AC solar section is going to join me, and we're going to stream the sun live into your home. So stick around. We'll have another live stream coming very shortly.